So I'm going to keep the structure for our class this week more or less the same in terms of what we're going to be doing, where we're just like kind of going through the slides and I'll give you problems to work on. The difference will obviously be instead of me just giving you time in class and then just waiting, you can just kind of like pause the video and take as much time as you need to attempt the problems before sort of starting up and watching me do the solution. So here's our warm-up problem that I think you should all try to do right now before you start watching the rest of this. Find all values of the constant k so that the following limit can be evaluated using L'Hopital's rule. And so it's the limit as x approaches the value of k of x minus k over x squared minus x minus 6. So pause the video and then come back to this. So if x is approaching k, then our limit would be of the form k minus k over k squared minus k minus 6 should be 0 over something. And so if we're going to be able to evaluate this using L'Hopital's rule, then this has to be of the form 0 over 0. And so k squared minus k minus 6 has to be equal to 0. So we basically just need to solve this quadratic equation, which we could do by either using the quadratic formula or just by factoring it, which is what I'm going to do. So you could try k minus 6 times k minus 3 times k plus 2. Let's see if I do this right. This times this equals negative 6. Negative 3k plus 2k is negative 1k, so that looks good. So our 2k values would be equal to 3 and negative 2. All right, so those would be the constants that allow us to evaluate this limit using L'Hopital's rule. If you were to actually do it, so we're not being asked to actually evaluate this limit, but let's just do it for practice. So this would be equal to, via L'Hopital's rule, the derivative of the top, which would be 1 over 2x minus 1. And so this would be equal to 1 over 2 times k minus 1. So we're just replacing x with k. This would be a problem if our denominator was equal to 0. If the denominator was equal to 0, this limit would end up being like undefined. It'd be like infinity from the right and negative infinity from the left. But k can only be equal to 3 or negative 2 anyway, so this is either going to be equal to 1 over 2 times 3 minus 1, which is 5, or 1 over 2 times negative 2 minus 1, so negative 5. So it's either going to be 1/5 or negative 1/5. But here, at this point, we're just doing more than we're asked. All right. So 4.7 is on optimization. So the whole point of a lot of what we've been doing in this chapter is we can find like maxima and minima for our functions given certain things. And so maximizing or minimizing things is a very common thing that actually happens in the real world, where we want to maximize our profit or minimize the amount of material we're using given like some constraints on what material we're allowed to use, or it has to be in the form of a box or something like that. So the whole idea of this chapter is we have something which we want to either maximize or minimize, which will basically get something that we can take the derivative of and find critical points for. And we'll also have some constraints on that thing that we're trying to optimize. Say we're trying to optimize area, maybe like our area has to be constrained by the fact that it has to be in the shape of a square or something like that. Or maybe the perimeter has to be equal to like 10 meters of fencing. So let's say that we have 300 feet of fencing and we're enclosing a rectangular area. And let's try to find the length and the width of the largest area that we can enclose. So your intuition should probably tell you that if this is going to be a rectangular area, that if you use a small and skinny rectangle, that's not going to give you as much area as just like a square would be. So like your intuition should probably be telling you that the best way to maximize area would be to use this 300 feet of fencing as a square. But let's use calculus to actually justify this for ourselves. So let's call this x and this y. So we have 300 feet of fencing. So x and y, if we use those variables, the perimeter in terms of these variables has to be equal to 300 feet. So the perimeter has to equal 300 feet. The perimeter, though, in terms of x and y, is just equal to, well, we have x up here and then y over here as well. So we're going to have 2x plus 2y for our perimeter. So 2x plus 2y equals 300 feet. You could simplify this. You could just divide by 2 on both sides just to make our equation a little bit nicer. So I'll do that. X plus y is equal to 150. And we are trying to enclose the most amount of area as we can. So we are trying to maximize a function, which I'll call, well, okay, I won't call it a function yet. We're just trying to maximize the area, which is not going to be yet a function of just a single variable. But the area in terms of x and y is just the length times width is just x times y. It would be great if we had a formula for our function that only had a single variable, right? It would be great if you could say that our area was like 2x squared plus 5x plus 3, because then you could take the derivative of that, find critical points, and do the stuff that we've been doing so far. But we have two variables, so how do we deal with a second variable? Well, how we deal with that is we use this information up here. So we can use this equation up here to eliminate one of the variables and have this expression completely in terms of a single variable. So let's say that I want this to be totally in terms of the variable x. Well, then up here, I can solve for y just by subtracting x on both sides and get y is equal to 150 minus x. And then I can replace y with what we just found, 150 minus x. So now this is a function of x, so I can write the area as just a of x. Can't really do that up here because there's an x and there's a y over here. There's two variables, but over here it's just a single variable. This is a function of x. And this function of x, we can now use calculus to find our critical points and kind of go from there. So let's see. So area is equal to 150 times x minus x squared. If we were to distribute that x, we can find critical points, which would be 150 minus 2x for our derivative. And to find our critical points or our critical numbers, whatever, we set this equal to 0 and solve for x. 150 is equal to 2x, and so x would be equal to 75, just dividing by 2. 275. Okay. Cool. So that's our only critical point. We don't necessarily know that this is going to be a maximum or a minimum. There's two ways of kind of thinking about this. You could do a first or second derivative test to check if it's a local min or max, or you could think about this in terms of endpoints. So x and y have to add up to 300 feet. They also have to be, they can't be negative numbers. It wouldn't make sense for x to be a negative number and y to be a negative number. So the largest that x could be would be 150. So the smallest that x could be would be x equals 0. So x could be 0 and y could be 150. And so then you'd have 2 times y equals 150, but then, it'd just be like two 150 long fences just like placed right next to each other. Or if x is 150 and y is 0, then that would be your other endpoint. So for both of these endpoints, the area is going to be equal to, well, I don't need to write it as x times, or, okay, I could just do this, yeah. So it's going to be 0 times 150 minus 0. If I were to plug in 0, and if I were to plug in 150, then I would get the same thing. If I get 150 times 0, so we get 0. Okay, so for both of these, the area is equal to 0, and then the area, if x is equal to 75, would be equal to 75 times 150 minus 75. So this is equal to 75 times 75, or 75 squared. I don't know what 75 squared is. I just kind of want to know. $5,625. Square feet. Okay, so if you recall, we to find a maximum and minimum value for our area function, we just find all of our critical numbers and plug our critical numbers and our endpoints into our function, which we're trying to maximize, and then just pick the biggest value. And then obviously this is going to be the largest value, and the smallest that you could get would be 0. So this is the maximum area that we can find, and the length and the width of the largest area we can enclose would be, well, the length would be x equals 75, and the width would be y equals 150 minus 75, which would also be 75. So here's a self-check question. Let's say that we want to find the point on the curve y equals 3 root x that is closest to the point 7, 0. Which of the following would help us reach that goal? Do we want to minimize the expression square root of x squared plus 9x? Do we want to maximize that expression? Do we want to minimize this expression, square root of x minus 7 squared plus 9x? Or maximize that expression, or none of the above? So pause the video and think about it, and then unpause, and we'll discuss. So the point 7, 0 is over here. And here's our curve, y equals 3 square root of x. And we are trying to minimize the distance from a point on this curve to the point 7, 0. So we want to minimize this blue distance right here. Okay. How do I find that blue distance? So basically, if we want to find the point that is closest to this point, we're really trying to find the x value that minimizes this distance. What is this point over here? So this is the point on the curve y equals 3 square root of x. So it would be x comma 3 square root of x. So we just have some arbitrary x value, and then our y value would just be given by this formula. Okay, so then if we were to compute this length right here, all we have to do is use the Pythagorean theorem. So, okay. All right, so we have to compute this length right here, and then we have to compute this length right here, and then we can use those to compute this distance right here, which we'll call d. So this length up here, this vertical height, is easy to calculate because this is just how high up on the curve we are. So that's literally just going to be 3 times the square root of x. So this is just 3 root x. And then this bottom distance over here, this is going to be this x value minus this x value. So this minus this. You could think of that as this is 7, and this is x. So 7 minus x is equal to this leftover part right here. So this is equal to just 7 minus x. And so by the Pythagorean theorem, the distance squared, d squared is equal to 3 root x squared plus 7 minus x squared. So it's equal to 9x plus 7 minus x squared. And then we just take the square root of that, so the distance is just equal to this. Okay, so yeah, we get 9x plus 7 minus x squared, and then take a square root. I have it flipped, so it's one of these two things, and we are trying to minimize this expression. Okay. Cool. So yeah, the answer is C. All right, so let's actually do it now. All right, I'm just gonna copy this over so that I don't have to do as much work. Great. All right, so this is our distance function. I could call this like d of x if I really wanted to. It doesn't really matter that much, but I'll do it. And this is also, I could also just write this as 9x plus 7 minus x squared to the 1/2 power. And so we now need to take derivatives, find critical points, yada yada. So d prime of x, derivative of something to the 1/2 power, is going to be 1/2 of that something to the 1/2 minus 1 power, so negative 1/2 power, and then times the derivative of this inside function. Derivative of 9x is just 9. Derivative of 7 minus x squared is what? Well, this is something squared, so derivative of something squared is just 2 times that something, times the derivative of the something, which is just negative 1. So this, I believe, is our derivative. Let's see if I did that right. All right, so bring that. That's negative 1/2. This is the same as that. This derivative 9 plus 2 times that times negative 1. All right, so I think I'm good with this derivative. And now let's maybe try to clean this up a little bit. So I'm going to bring that 9x plus 7 minus x squared to our denominator. And what about for our numerator? So this is equal to, so this will be our new numerator, right? So this is 9, 9, and this negative makes this minus 14 plus 2x, so this would be negative 5 plus 2x, or 2x minus 5. Is that right? So positive 2x minus 14 plus 9, negative 5. Okay, good. All right, so we're looking for places where the derivative is equal to 0 or if it's undefined. So we want to know when is this thing equal to 0 and when is it undefined. So if we're looking for it's equal to 0, then we would just want 2x minus 5 equal to 0. And so x would be equal to 5 over 2, or just 2.5. So that would be one of our critical points. And then we could also look for when the denominator is equal to 0. So we can just ignore the 2 because we're setting it equal to 0, right? So 9x plus 7 minus x squared equals 0. We could just square both sides. It's not going to really change anything. And then I can take this 7 minus x squared and distribute all that. So that's plus 49 minus 2x plus x squared equals 0. So this would be x squared plus 7x plus 49 equals 0. And I have a feeling that this is just never going to equal 0. we could see that with our quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And if we look at inside of here, 49 minus, this is 4 times 49. This is going to be like the square root of a negative number. And so this is not going to give us any real numbers, so we don't get any critical points from this. So 5 halves would be our only critical number. And now we just need to know, is this going to be a minimum or a maximum? So are there any logical endpoints here? So certainly 0 is a logical endpoint. But there's no like right-hand endpoints. So we're not on like a closed interval. It's not like we're on the closed interval like 0 to like 50 or something like that. We're really on 0 to infinity. And so we don't have closed endpoints on both sides. So we're just going to have to sort of analyze this using derivatives. So let's do our first derivative test where we take our 5 halves right here, and then we'll just take points to the left and to the right of that. So this is like 2.5, so I'll pick like 1, and then I'll pick 3 and plug those into d prime. So d prime of 1, we could just use this formula because it looks a little nicer. D prime of 1 is equal to 2x minus 5, so 2 minus 5, which would be negative 3, over 2 times the square root of like some positive number. So this whole square root thing has to be positive. I don't really care what it is. So this is going to be negative, right? And then d prime of 3 is going to be 2 times 3 minus 5, which is equal to 1, over 2 times the square root of like some number. So this is going to be positive. So it's negative here, it's positive here. So it's going down, and then it's going up. And so that tells us that this is going to be a minimum. So the point on the curve, the x value that is going to get us there, the x value is 5 halves. What would the point itself be? Because remember, a point is just an x value combined with a y value. Well, the y value is just given by this, so just 3 times the square root of our x value. So 5 halves, comma, 3 times the square root of 5 halves is the closest point to 7, 0 on that curve. Awesome. Here's another one. Let's construct a rectangular box with a square top and bottom. The material for the bottom and the top costs $1 per square foot, and the material for the sides is $2 per square foot. If the box must have volume 20 cubic feet, and the dimensions of the box, so we want to find the dimensions of the box that minimize the cost of the materials. All right, so let's draw a box here just so we can sort of intuitively get what's going on. Boop, boop. That. Okay, so there's our box. Okay, square top and bottom means that this and this are both the same. So we'll call that X. Okay, but it's a rectangular box. The top and the bottom are square, but it could be like more like, oh gosh, it could be more like rectangular. All right, that's not what I want. I'm giving up on that. It could be like a more like rectangular box, something like this, where our height is just varying. So let's call that the height of the box. I don't know, maybe Y makes more sense. I'll stick with H, whatever. So let's call our height H, which has to be different from these, or it might be different from these X values. Could be the same, we don't know. And let's now try to figure out the two things. that we are trying to maximize or minimize, or minimizing the cost. And then the other thing is, what's our constraint? Our constraint is that the volume is 20 cubic feet. So constraint is the volume equals 20 cubic feet. And what is the volume of this box? It's x, it's base times width times height, or length times width times height. So x times height. I'm just going to write that as x squared times height. This is the area of our base times height. And that has to be equal to 20 cubic feet. And we are trying to minimize the cost, which is equal to what? So the top costs $1 per square foot. So we find the area of the top and the bottom, and then multiply that by 1, or $1 per square foot. So the top and the bottom both have area x squared. So we have x squared times like $1 per square foot. And then we have 2 of those for the top and the bottom. I'm not really going to go through writing all that. I'm really just going to say we have 2 times x squared times like 1 or whatever. So that's our cost for the top and the bottom combined. And then what's our cost for the sides? So each side, the area of each side is going to be x times h. And how many sides do we have? We have 1, 2, 3, 4 sides. So 4 sides. And each side is going to cost $2 per square foot. So this is the total square footage of our sides, and then multiply that by $2 per square foot. Okay. All right. Now we need to get this totally in terms of either x or h, and it doesn't really matter which one we do. We generally will just pick whatever one is easier for us to figure out. In this case, since x squared times h is equal to 20, it's hopefully clear that like solving for h is easier than solving for x, because if we solve for x, we'll have like a square root in there. So our constraint tells us that h is equal to 20 over x squared. You could write that as 20x to the negative 2. I'm probably going to do that because we're going to do some derivatives pretty soon. So our cost function is now going to be totally in terms of x. If I do that, it's going to be 2x squared plus, I'm going to combine this 4 and the 2 into 8. 8x times 20x to the negative 2. That's h. So this is equal to 2x squared plus 160 times x to the negative 1. Now I need to take derivatives. So c prime of x is equal to 4x minus 16x to the negative 2. Great. And we want to set this thing equal to 0. So what's the easiest way to go about doing this? Do I want to combine that, or do I want to do that? Okay, I'll just combine that into a single fraction. So this is like 4x cubed over x squared. So 4x is equal to 4x cubed over x squared, right? And this is equal to 16 over x squared. That's equal to 0. And so I could then make this 4x cubed minus 16 all over x squared, set that equal to 0. So places where this derivative is either 0 or undefined. So it's definitely undefined at x equals 0 because our denominator would be 0 at that point. And then also we need to look at, I think it's going to be like the cube root of 4 or something, because we want 4x cubed minus 16 equal to 0. So x cubed minus 4 is equal to 0. So x cubed is equal to 4. So x is equal to the cube root of 4. All right. So x equals 0 is like barely going to be a critical point. We're not going to consider any negative x values here. So really, this is our only point of interest for this problem. So we go to our number line test. So let's do cube root of 4 right here. And then we'll pick something to the left of that and then to the right of that. And then, 0 is going to be over here. So we don't want to pick, so 0 kind of is a critical point. So we don't want to plug that into our derivative. We want to plug something that's like between 0 and the cube root of 4, and then something that is to the right of cube root of 4. Because again, x values of 0 or less are just not going to make sense in the context of our like rectangular box. All right, so let's see. Cube root of 4 is bigger than the cube root of 1, which is just equal to 1. And the cube root of 4, what is that less than? Well, you could just say it's less than 4, right? Is there an easier number? Yeah, I'm just gonna do that. All right. Cool, and let's plug those into C prime. So C prime of 1 is equal to 4 times 1 minus 16 times 1 to the negative 2. So I'm plugging into here. So 4 times 1 minus, and this is really like 16 over 1 squared. So minus 16. So this is going to be negative. C prime of 4 is going to be 4 times 4 minus 16 over 4 squared, which is 16. Okay, so this is going to be like 16 minus 1, which is 15. So this is going to be positive. All right. Good. Okay. Sorry, I'm just kind of like checking things in my head and making sure everything's working right, because no one's here to tell me I'm doing anything wrong like normal. All right. Cool. Hopefully there's no like typos or anything in this video. It's nice to have the class there to just catch silly mistakes. All right, so this is going down and then it's going up. And so yeah, this would be a minimum. All right, great. So x equals cube root of 4 minimizes costs. We also need to know what our height would be. Our height is just given by this, just 20 over the x value squared. So height would be 20 over the cube root of 4, but then square it. Also, we should probably put our units in here, so these are both measured in feet. All right. Let's now find the area of the largest rectangle that can be inscribed in the region bounded by y equals 3 minus x over 1 plus x and the positive x and y axes. So I'll let you try this one. So this one is going to be similar in spirit to the one that we did back here. Where like, okay, so just to kind of like remind you what happened a little bit. We found a point on the curve. The point on the curve was just, you had your x value and then your y value was just given by like the function, because it's, on the function's graph. And then you could like compute a certain thing. So we're trying to minimize like this thing, which we can find by just using like the Pythagorean theorem. And then we just get the lengths of these just by using this, and then like some basic like subtraction, like 7 minus x to get this distance, and then just 3 square root of x to get that distance. And then this was like the thing that we're trying to minimize there, that Pythagorean theorem thing. So this is similar in spirit to what happens here. So we have this curve right here. So this is the curve given by this function. And we have this region that's in this rectangle that is inscribed by, it's bounded by the x and the y axes. And then we take a corner point that just lies on the graph of the curve, or the graph of the function. And then we just make a rectangle out of those sides or whatever. So then we take the area of that rectangle, and then we want to maximize that area. So take a couple minutes, pause this video, and give that a shot, and then unpause, and then see if you get it. So all right, so let's call this length x, and I guess we'll just call that length y, but we can also just call it, our y value is just going to be given by this. So technically, like, this is just giving us our restraint right away. And so our area is just equal to our x value times our y value, which is just equal to x times 3 minus x over 1 plus x, which is equal to 3x minus x squared, or maybe I should just leave that factored actually. So x times 3 minus x over 1 plus x. So this is our area function in terms of x. And we just need to maximize this. Also, this graph I think might be, is it misleading? I can't tell if the graph actually crosses through the x or y axes. So if it does kind of cross through the x and y axes, that would give us like our obvious endpoints, but I don't want to go through the trouble of finding those. We'll just kind of do this more using derivatives and stuff. All right, so a prime derivative of the top, maybe I should have distributed this for the derivative. So 3x minus x squared for 1 plus x. All right, so the derivative of the top is going to be 3 minus 2x. Keep the bottom the same. So we're doing quotient rule here, right? F prime g minus fg prime. So minus derivative minus the top, keep the top the same, times the derivative of the bottom, and the derivative of the bottom is just 1, so that's nice, all over the denominator squared. All right. Now I will distribute everything. So this times this is equal to 3 minus 2x plus 3x. So that should be plus x, right? Minus 2x plus 3x equals plus x. And then minus 2x squared. And then minus 3x plus x squared, just distributing this negative to both of those terms. I will keep the denominator factored like so. Now I'll combine all my x squared terms. This plus this is equal to negative x squared. X minus 3x is equal to negative 2x. And then, let's see, I only have the plus 3 left. Can I factor that? Let me just pull out a negative. X squared plus 2x minus 3. This is just for some reason easier for me to see how to factor it. So this would be negative x plus 3 times x minus 1. Does that work? So 3 times negative 1, good. And then 3x minus x equals 2x. All right, good. All right, so this would be our derivative. And if we want to know when this guy is equal to 0, or when it's undefined, we would look at when the numerator is equal to 0. So that would be when x equals 1 or -3. So this is when a prime equals 0. And it's undefined when our denominator is equal to 0. So that would be when x is equal to -1. Okay. We're not going to care about this -1 because we are specifically picking a point where x is positive. So we can also throw out this like -3, because again, we're only looking at positive x values. So we would hope that x equals 1 is going to give us a maximum value. It's possible that there is no maximum value, by the way. That is always a possible thing. It's possible that like you could just always make it infinitely bigger and bigger and bigger. I would find that unlikely in this case, just based off of the intuition and what the graph looks like. But let's see it anyway. All right. Made too much over here. Yeah, these problems take up a lot of space. I need to learn how to not trigger that. Okay. All right, so this just found our derivative, right? So here's x equals 1, and then here's -1 and -3 way over here, which we don't care about. I'll pick 0, or do I want to pick 0? I kind of just want to pick a positive. I don't think it's going to matter, but yeah, I'll just pick 0. I kind of wanted to like just pick a positive value because we're trying to stay in the positive in the first quadrant, but I don't think it'll matter. Then I'll pick 2 over here and plug those into a prime. So this is our formula for a prime, right? So -0 plus 3 times 0 minus 1 all over 1 squared. So this is equal to +3. And then a prime of 2 is equal to -5 times 1 over 3 squared. And this is negative. So this is positive and then negative. So positive and then negative. Okay, and that's good because that looks like that is going to maximize it for us. Okay, so x equals 1 maximizes area. So what is our maximum area? Well, this is the x value that maximizes the area. The maximum area is just given by the x value times the y value, which is just x times this whole thing. So 1 times 3 minus 1 over 1 plus 1, which is equal to, okay, this is 2 over 2. 2 over 2 is 1. 1 times 1 is 1. So this would be our maximum area. All right. Great. All right, last problem for this this section. Let's say that you want to fence a rectangular yard up against a barn. If you have 300 feet of fencing available, find the dimensions that maximize the area of the yard. So I'm going to set up the picture and then I'll let you try it. So it's being set up against a barn, so we only need 3 of the sides. So our barn is going to be like over here or whatever. Maybe I'll just draw it red. Barns are red, I guess. Here's our barn. And then our rectangular fence will look like this. And like that. And then like this. Nope. Okay. All right, so here is our fence. It's just 3-sided. We're going to have, we'll call this x and we'll call this y. Call them whatever you want. So pause the video, figure out what would your constraint be, what would the thing that you're trying to maximize be. Can you get that into a function of only one variable? And then from there, can you actually find that maximum, or can you find the dimensions that maximize that area? Find the x and the y value. So pause that and then come back. I'm just going to start now. All right. So we have 300 feet of fencing available, so that's going to be our constraint. So 300 is equal to the sum of these three side lengths. So it's going to be, we have, this is x, and then we have y. So we have 2x plus y is equal to our amount of fencing. And we are trying to maximize the area. The area is just equal to the x value times the y value, which we now want to just get into a function of one variable. So let's maybe, it looks like it's easier to solve for y, so I'm going to do that. So y is just equal to 300 minus 2x. So if I replace y with 300 minus 2x, that would give me a formula for the area totally in terms of x. I can then distribute that x and then take a derivative to find critical points. So I get 300 minus 4x and set that equal to 0 to find my critical points. I don't have any undefined points here or anything, so I don't have to worry about that. So 300 is equal to 4x. So x is equal to 300 over 4. 300 over 2 is 150. 150 over another 2 is 75. So x is 75 feet. And then y would be equal to 300 minus 2 times 75, which would be equal to 300 minus 150, which is also equal to 150. So y would be equal to 150 feet. This would be 150, and x would be 75. So you have 75 feet here, 75 feet here, and then 150 here. That adds up to 300, so that checks out. And then the area would just be 150 times 75. We're not asked to find the area in this one, we're just asked to find the dimensions. So that would hopefully be our answer. And we want to also, check that this is actually going to be a maximum. And let's see, I think I'm going to actually do the second derivative test here, because I think the second derivative test will be really easy to apply here. So what's my second derivative? My second derivative is just equal to -4. So it's just straight up always concave down. So it's always concave down. And then, so a double prime of our critical point, which was 75, is also equal to -4, because it's always -4. So it's concave down. And so, flattens out like here. So x equals 75 is, in fact, a maximum. Awesome. So that's it for this section. Join me on the next video for the next section. So we'll have 3 videos for the 3 sections this week.